Recording in progress.
Okay, thank you here for coming. It's a pleasure to introduce you to Christian Beck, who most of you already know him. He's been a visitor to IFES several times. He's at the Queen Mary University at the School of Mathematical Sciences, and he has a background in statistical, nonlinear physics, complex, also a past in dark energy and other more maybe static stuff. He's well known for work on super statistics, non-extensive systems, and other things. And he has moved more recently to more real-world applications like the power grids or data on air pollution and other things. I had the good opportunity to share with him 6 years at the board of the European Physical Society, of the Statistical and Nonlinear Physics Division of the European Physical Society. He was the chair. I was just a board member, and he did an excellent job there, I can tell you. During that time, the prize, the European, what's the name? The European Statistical and Nonlinear Physics Prize for the European Physical Society was established. And there was a conference organized every 2 years. I think that has been a big boost to the field of complex systems. Okay, today he's going to tell us about these data-driven load profiles and the dynamics of electricity consumption.
Thank you very much for this very kind introduction. For me, it's a great pleasure to be here again, meet so many old friends, and it's fantastic. And one of the reasons I'm here is actually that I wanted to discuss with the experts you have here on power grids, which is Per and Damia, and I benefit so also very much from their experience in writing grant applications for power grids, indeed, because to be honest, it is my interest in power grids is also there because we have lots of funding opportunities these days in the UK to understand power grids if they have a high degree of sustainable energy generation in them, like wind energy or batteries or solar panels. So, but it also leads to interesting complex physics, and that's what I want to talk about. So in particular, I want to talk about data-driven load profiles and the dynamics of electricity consumption, because the human component of electricity consumption is maybe the most complex one, because human beings, they are very correlated sometimes and not at all statistically independent random variables, how they behave. So you will see that in this talk. What I want to talk about is first a little bit of basic ideas of what new phenomena we expect in systems, in power grids with a high fraction of renewables. And then I will talk a little bit about the statistical analysis of frequency fluctuations in various types of power grids, because the frequency in a power grid is a very interesting variable. It kind of represents the balance between production and demand, right? So if there's a lot of demand, then the frequency drops a little bit down from the 50 hertz that you normally have. And if there's plenty of energy in the system, then it's a little bit above 50 hertz. So the fluctuations around the 50 hertz that you can measure in every socket here, actually, they are very, very interesting variable to make models for. Okay, so let's look at that. Well, you all know we are currently in an energy transition. We want to lower the carbon footprint, and the power grid of these days looks very different from what you had 20 or 30 years ago, where you had a very big power plant that was producing a lot of CO2. And now it's more that you have little units here and there, some wind farm here, some solar panel there. So overall, the power grid is becoming a much more complex system with little units everywhere that have lots of fluctuating properties. So the wind is not blowing constantly. The sun shines sometimes more than on other days. Today it doesn't shine so much, actually. Okay, so therefore, as said, we want to understand the stability, so to speak, of these power grids, because that's not at all taken for granted. If you replace one big plant by lots of complex units, it's not clear whether the system stays stable. From the modeling point of view, there are many, many models to look at for power grids. Maybe we start with the very basic model, the swing equation, that is, so to speak, the simplest model you can think of for a power grid. It is basically, you look at this frequency and introduce a fluctuating term around the 50 hertz. The omega is the 50 hertz that you normally expect to get out of your socket. And then these fluctuations around the 50 hertz, the simplest model you can think of is such a differential equation here. There's some feed-in of power produced by the various sources of power in the system. Then there's a damping term, and that damping is influenced by people who control it, if there's a control. And then there's a coupling term of various nodes. So if you label your power grid by node I, then the simplest coupling term you can imagine is this sort of coupling term, which looks very familiar to people working in complex systems. So you have many equations that have such a coupling term. And you see, of course, if all frequency at every place are the same, then this term vanishes there. So for the power grid, of course, we want a stable state. We want synchronous behavior. We don't want any chaotic behavior, although it might be interesting from a dynamic systems point of view. And as said, if you can really measure that now very precisely, this time series theta of t, and if the frequency is below 50 hertz, it means there's a lot of demand in the system, and the turbines work hard, more power production is needed. And if it's above 50 hertz, there's less demand and a surplus of power. It's actually, and then if in the second state, the companies really want to get rid of power. So it's funny, the prices of electricity can sometimes also be negative because they want you to get rid of the surplus of power you have. So prices for electricity are also a very interesting subject area that is being modeled. Good. And why I mentioned the grants. Of course, there is technical. You want to get a nice big grant that is funded, but also from a theoretic point of view, I like power grids because they are the largest machines on Earth. I mean, if you ask somebody what is the biggest machine on Earth, they might talk about CERN or the LHC or so. But the power grid that lasts from over the whole range of Europe, that range is enormous. It's the biggest machine on Earth you can imagine, but it's also the most complex one you can imagine because it's intrinsically coupled to the consumers, right? The power grid with the consumers is something extremely complex, so it's something that is really worth looking at research-wise. Good. So my involvement with that started about 6 years ago when I was visited by a young PhD student at that time, Benjamin Schäfer in London, who is now a professor in Karlsruhe. And so we had the idea, let's look at real data, right? And these data there weren't so many people looking at actual data. They thought it's just trivial and just 50 hertz and that's it. But the fluctuations around the 50 hertz that you can measure are really quite interesting. So here you have the time over 1 day. Here's the 50 hertz and the signal that you can measure if you have a suitable device. Plug it into your socket is something like this signal here. So on average, of course, it's 50 hertz, but then there are rapid fluctuations. And also there are daily fluctuations as well that you see from the gray area there. So sometimes at some days it's a bit higher, a bit lower. And if you look at that signal in a more detailed way, here's the time over 1 hour, then you see here there are every 15 minutes some jumps in the signal. Yeah. What is the gray and the yellow one is it's kind of the probability density. So it's the maximum of the probability density that is in yellow here. The gray area is the entire region that that this signal can take on. I have to look up precisely the color coding that I can't remember anymore. But you see the gray area is the fluctuations that you can expect from this signal, whereas the yellow area is sort of the typical behavior that you have over a day. And then what you see here is every 15 minutes there's a jump process. So this process is apparently more complex than what we normally model in statistical physics. It's not sort of a continuous type of Brownian motion, or so it's something more complicated with jumps in between. And these jumps every 15 minutes are produced by the markets, the electricity market, at least in the UK and in Europe. Every 15 minutes has a new company can feed in some energy. They win a contract to do that. And therefore, every 15 minutes, things change. So it's a stochastic process that is not the usual type of stochastic process you expect in statistical physics. So there's also an interesting thing to observe here, namely, we talked about the gray area, which is like the variance of this signal, the size of this gray area. And you see here, for example, the variance is smaller, and here the variance is bigger. So it's a process where the variance of the process itself is a random variable that changes on a bigger time scale. Like in finance, where you have stochastic volatility models, the volatility is like a variance parameter. That is also the case here. For 15 minutes, you have that variance, then for another 15 minutes, a bigger variance. So that makes it an interesting stochastic process. Yeah, that's also true. It's non-Gaussian and in particular not symmetric. Yes, you're right here. Yeah. So a lot of things that one needs to take into account when you want to model that. And here's you see the main problem is, of course, people often think of these types of random fluctuations as Gaussian, but they are not Gaussian in the power grid. Here you see a typical histogram of the frequency in a logarithmic scale. If it were a Gaussian process, then the logarithm of a Gaussian is just a parabola, and that would be this orange line. But the real data are much better fitted by this blue line here. And what is the blue dotted line is what we call a Q-Gaussian. You will see the formula very soon. You could also think a priori of stable processes, a Levy type of processes, but they would generate this PDF, this dashed green line. And the stable alpha stable processes have two heavy tails. So it's somewhere in between alpha stable and Gaussian. And these Q Gaussians seem to be a very good fit of the data. So let me explain to you what these Q Gaussians are. It is just this formula here. They, as Raoul mentioned, they occur sometimes in non-extensive type of models. So take for the energy that you have here a quadratic function, so a half x squared, like kinetic energy for a free particle or so. Then that would be the formula for a Q Gaussian. So a Q Gaussian is in reality a power law. You see, for large values of x or e, this decays like a power law with an exponent 1 over q minus 1. So it has heavy tails, and it fits these data pretty well that you see in power grids, but also in other systems very often. And so why could we see these Q Gaussians? Perhaps that is the basic idea of what we sometimes call superstatistics. So you have a superposition of different statistical mechanics with different inverse temperatures, if you like. If you do ordinary statistical mechanics, you would have just the Boltzmann factor e to the minus beta e. But in a superstatistics, you assume you have a non-equilibrium situation where beta has spatial temporal fluctuations on a big time scale. And then what you do is you kind of average all these local Boltzmann factors and weight them with the probability f beta to observe a particular beta in a certain region of the space. So that is this probability density function f of beta for the parameter beta. And then in the long term, you expect that you see a mixture of all these different Boltzmann factors in the system, because the temperature is not constant really in this model. So beta is distributed with a distribution. And if you choose now for the f of beta, a very common distribution, the so-called chi-square distribution, for which you have the formula here, it's just a gamma distribution. So it's beta to some power times e to the minus beta. If you assume that distribution, then by integrating over all beta in the system, so you get this Q exponential or Q Gaussian out of this integration. So that is the main idea of what people sometimes call a superstatistics. You have a superposition of different statistics where a parameter that is normally held constant, like the inverse temperature beta, is distributed. And that leads then quite naturally to Q Gaussians or power laws if you start originally from a Gaussian here, right? So that idea we applied then also to the power grids. And but for that, you need to have then a kind of local dynamics for your frequency fluctuations. So in the simplest model you can think of would be that the frequency deviation relaxes here with the damping term and is driven then by Gaussian white noise. That would generate a Gaussian process, the Ornstein-Uhlenbeck process. But if you now assume that this sigma, this volatility parameter, the strength or the variance of the signal is also a random variable, which this sigma is basically given by the beta above here. So if you integrate then over these fluctuating variance parameters, you end up quite naturally with Q Gaussians in the system. But that is only the simplest model you can think of, and there are many, many more models of what frequency could do, including the jump processes that I described before. So let's therefore look at experimental data. I already showed you the Q-Gaussian is well fitting the data, but there are, of course, much more observables you can look at. For example, the correlation function, the two-point correlation function. If you have a given stochastic process, then you can distinguish between different stochastic processes by looking at the two-point correlation function. So you would look at the frequency deviation at time t times the frequency deviation at some later time and normalize that thing. And for a Brownian particle Ornstein-Uhlenbeck process, that would be simply an exponentially decaying function. But what is it for power grids? Well, and there are now new data really that are worth looking at. And the main result is every power grid is different. So here you see, as we are on Mallorca, let's look at the blue line here. Your power grid looks like this blue curve here. Looks actually quite nicely like exponentially decaying correlation function, whereas in the UK, let's look at that. Our correlation function decays much faster than yours, and then later they look similar to Mallorca here. But then look at other systems like Central Europe. You have these dips here in oscillations in the pattern, which comes from the trading that is taking place there. So every power grid seems to be distinguishable by features in the correlation function. Okay, so so the idea was then, okay, we have these different power grids. Can we make a model to reproduce then a given measured correlation function, including the density of the fluctuations? And that can be done. So you can look at more complicated models. But of course, the drawback is you plug in more fitting parameters as well. But look, for example, here is one of these models that we then developed in that paper that generates the orange line. And here's the correlation function in green, the measured correlation function. So more or less, you can qualitatively describe the correlation functions correctly, but there are still differences, right? So it's not perfect what the models can do. And that was part of that paper. Then another question you might ask, I talked about the super statistics. So you saw that the chi-square distribution for f of beta does a good job to generate Q-Gaussians that fit the data well. But other power grids are a little bit different sometimes, and you see with an algorithm, we are able to extract the f of beta out of a measured time series. So we assume there's a super statistical process, and we have some algorithm to extract the f of beta then. And then you see the distribution that you get there is sometimes a bit different. So for example, here you see data for the Japanese power grid, which seems to be a little bit different. So those data are best fitted by a log normal distribution here, the blue curve, whereas the European data, for some reason that I don't know why, are better fitted by chi-square distributions. So every power grid has some sort of specific characteristics, which depends on the vector of sustainable energy sources that you have. For example, in the UK, we have much more wind than somewhere else. And it also depends on the size. I think your power grid here in Mallorca is pretty independent on its own. You have a connection to mainland Spain, but more or less your power grid does what it wants on its on its own, yes. So it's a smaller power grid in a sense, so it has different characteristics than other power grids. Yeah, so yeah, talking about the islands, we looked in particular at small islands like Iceland. I think, Per, you have also done work on islands, is that correct? Yeah. And what we found there is that for smaller islands, the tails, as you might expect as a complex systems physicist, smaller islands, you expect bigger fluctuations, perhaps, because it's not so many components. So indeed, for Iceland, you see there are heavy tails there, heavier than for big power grids in the distributions. And yeah, so it's funny, if you look at a church in Reykjavik, they seem to already expect this pattern there when they built this church. Okay. Then another thing, so my collaborators there, young guys who do a lot of machine learning and modern methods in AI and so on, all nice, but they thought we need some sort of more universally accessible database, because if you write to an electricity company, they are very picky about sending you data. They don't want that so much. Maybe the data are revealing how unstable their system is. But with these simple devices that were developed there in Karlsruhe, you can measure all these power grids very easily. Yeah. I have an admin meeting right now at Queen Mary. I'm very happy that I'm not there. Oh. Yes, but they know I sent my apologies to them. They know that I'm here. Yes, yes. Okay, so you see, we created a database where you can, at least if you're a little bit working in machine learning or so, it should be very easy for you to get these data and construct a good model for given power grids or so. And you see then that database is described in that paper there. So you see then, there's also another interesting point. In the early days, when I was working on non-Gaussian stochastic processes, we often applied it to turbulent flows. In hydrodynamics, you look at these fluctuating signals, and you see that in turbulent flows, very often you have non-Gaussian behavior if you look at velocity increments, right? So rather than directly measuring the particle velocity of a particle that is embedded in the turbulent flow, you very often look at the difference of velocity on a given time scale, tau, and that you can do for these power grid signals as well. What is the statistics of the frequency difference on a given time scale tau? And then one knows from turbulence, the smaller the time scale, the bigger the tails become in your probability density. And that is also seen here for the power grids. You see, if you look at the excess kurtosis, which is describing how much your signal differs from a Gaussian distribution, then on small time scales, that is much bigger than on big time scales. Very similar to turbulent flows, actually, in their characteristics. But you see, again, that islands like Mallorca or Iceland, they have much heavier tails than continents, big power systems. Okay. Another interesting thing is about how does an instability in the system propagate through the system. So, for example, you may assume that here you have the big European connected power grid. You may assume there's a perturbation, let's say in Lisbon, and let's say a blackout there or a terrorist attack or whatever. And you see then a big perturbation in the signal in Lisbon. Question is, how long do we have to wait until through this complex machine, this perturbation propagates to Istanbul? And the nice thing is one has data for that, right? One can look at that. And so you can make then plots that show you the time a signal needs to travel to some other place at distance of 1,000 or 2,000 kilometers or so. And so what you see is a kind of a diffusion process, right? If it were propagating as a straightforward line, you would expect a linear relation between time and distance, so constant velocity, so to speak. But it is more this parabola, so the time grows quadratically with distance t proportional to d squared. That is a typical diffusion process, right? So your signal, although it moves in the power lines, it is diffusing in the system somehow like a diffusion process. Okay, so then another, this is on the size matters really for the power grid. Here's kind of the strength of the typical fluctuations in the frequency that we have around the 50 Hertz, given that we are either in a very small power grid. The smallest power grid you can think of is a microgrid, really, where people just are a few households together. But here we have very big power grids like the European one and Iceland is this, I think. And we, when we had this Marie Curie grant, Benjamin Schäfer was then a postdoc with me. We sent him to the Faroe Islands to make measurements because they have a really nice, very small power grid. And you see the fluctuations on these small types of islands are very big, and they seem to be following this fit here. So there's a square root of n. N is kind of, we approximated by the number of people living there, but in reality, of course, you want to estimate the size of the power grid, but that's a proxy, and you find a good fit by this formula. Good. So now I come perhaps to the most interesting of all this, namely the behavior of humans. And the frequency that we talked about is really influenced by two points. One is the production of energy. So wind energy, you have much more wind energy power production in the system if the wind is strong on that day. But the frequency is really influenced by the difference between demand and production. So if more people suddenly use power, that also leads to a dip in the frequency. And it turns out that this human component of power consumption is not much understood. And people use very, very old models for that. So let's look at a modern household. Typically, you would expect people these days, if they have a newly built house, they would have solar panels perhaps on their house, and maybe some also want to use a small wind turbine, so all should be environmentally friendly. They also have batteries and cars and electric cars. And so simply a lot of things have changed compared to 30 years ago. And the question is, how does now a typical household consume its energy? And so we looked at that, and it was quite interesting. Basically, the result of that paper was that what many electricity companies still assume in their user pattern is a bit outdated. So let's look at that. For example, here you see the power that is consumed over a 24-hour period, right? And the purple line here is the standard load profile that the German electricity companies are kind of using. They know, okay, yeah, at some time in the morning, of course, more power will be used and little power during the night. And there's a dip here over lunchtime. All that is known. So they have their load profiles. And of course, these average load profiles are important to know. But when you look at actual groups of households, conditioned that people live, let's say, in that area, then you see here the German households. I think that is the blue data, and the Austrian ones. They have very different consumption patterns. First of all, you see lots of fluctuations in these data. And also the average seems not to fit the standard load profile function that most electricity companies are using. And that is, of course, a very expensive mismatch, because dirt, and also environmentally very unfriendly, because a lot of dirty power plants are being switched on sometimes because it's expected there will be high demand at that time. But if you have the wrong average demand profile, that is simply a waste of energy resources, and also polluting the environment, because to cover the peaks, you need to switch on very dirty power stations, so to speak. So we think it's really important to update these types of average load profiles, which are sometimes 30 years old or so, to the current situation. And also you have to condition it on different types of seasons. For example, in the winter, you have a completely different demand pattern than in the summer. For example, you see here in the summer a peak that is produced by solar panels on roofs and things like that. And here's the point where I wanted to Perre and his group, and because in the new project that we plan, we will look also on consumption data of households in Africa. And if you condition now on whether people are poor or rich, you get very, very different demand patterns. And they are really important to understand these demand patterns if you want to decide on the stability of a given power grid. So much more research is needed. These are data for German, Austrian households, but every country is different. Okay, then the other thing is that, yeah, here you see some fittings. Machine learning is, if you like, a kind of sophisticated fitting method, and you separate the data into training data and validation data and test data, and you can then extract the optimum load profiles if you collect a lot of data, and that should really be done, because the better your load profile, the better you can optimize how much additional power you need to switch on. That is really good for the environment, and if you know that. And yeah, finally, the super statistical type of idea, you see them also here in the fluctuating power demand of the households. So as seen, if you have the time here, we have lots of fluctuations, much bigger fluctuations than people would normally expect. But some of these fluctuations are also correlated. For example, if there's a big football match, everybody goes to the fridge during the break, and so there's strong correlated behavior. And if 1 million people do the same thing, that has an immense effect on the power grid, on the energy consumption patterns. So we need to understand the people really to build the best stochastic models for these frequency fluctuations. And here you see the idea that super statistics is in a good first order model, if you like. If you look at such a time series that is really measured data, look at this box, for a while, there's hardly any fluctuations. The distribution is a very sharply peaked Gaussian, if you like. And then you go to a later time, and there is a much bigger variance in the distribution. So that is then a much broader Gaussian. And in total, if you add up, if you integrate over all these Gaussians of different variants, you generate heavy tails in the marginal distribution obtained by integrating over the entire system. So the idea is pretty realistic for real data. Okay, yeah. I'm already at the summary. We also want to have some time for questions. So I only talked about power grids here, but I think they're really an interesting system of practical relevance. What you see is the typical features of complex systems. They are non-Gaussian, they are correlated, they are highly complex, but we can use some things that were used 30 years ago in turbulence theory. We can use that now for these fluctuations in demand and in frequency signals. We can use that quite nicely. Yeah, and also this power grid deviation from 50 Hertz, it was a little bit not recognized as an important variable until recently, but it's an immensely interesting variable, right? In statistical physics, we measure the velocity of a particle or whatever, but what is that for these huge complex systems? And there, it's simply a good effective type of variable that you can look at this frequency, because it is incorporating both the production that fluctuates and the consumption that fluctuates as well. So it's a good effective variable to look at. And so it's a very informative variable, and one should better look at that also if one wants to develop more sophisticated stochastic type of differential equations that reproduce the data, then that is the variable to look at, really. Okay, we did similar things also, as Raoul mentioned, also for air pollution and water quality, where you have different types of time series, but can apply similar techniques. But that's basically all. And if you want to look up the references, they are there. Thank you.
Thank you for this interesting talk. Are there any questions, comments?
Yeah, hello. Thank you very much for the very nice presentation. I got confused at the beginning of your talk, in which you defined two different models. One of them had a coupling between the different frequency nodes with this sinus.
Yeah.
And then the second one was was this Ornstein-Uhlenbeck process with superstatistic.
Yeah. Yeah.
Are those two models related? Like I can understand the coupling as this superstatistic kernel or something like that? Or?
No, you're right. We the superstatistics is more an effective model. So I didn't really need the coupling of the different nodes that were in the original string equation. I put that equation more for historical reason why a lot of people start to work on power grids using that equation, and then they looked at the stability of that system, and then they made more complicated systems. But for realistic data, that swing equation, we are only interested in the stable fixed point of that system and tiny fluctuations around it.
I understand.
Yeah. So it's, your remark is good that in the sense the differences we see, let's say, in the correlation function and in various other obstacles you can look at, that also has to do with the topology of that network that you're looking at. And some power grids have better design than others. So that is in the coupling structure there, which you should do on the given topology of a given power grid. Yeah. So that is reflected there indirectly. But we then looked at data and tried to model these stochastic processes directly with.
Okay. No, very interesting. And also is not that related, but last week we had another talk about fluctuations in microbiota. And there is a lot of works on, there is a huge debate about how to explain the stationary fluctuations of microbiota around a fixed point.
Mm-hmm.
And it really much remind me to your work, because they have this kind of the same bell shapes that's
Okay.
like these charts. I don't know if you
Yeah.
are aware to these things.
Yeah, well, these ideas are applied in many different systems. So the superstatistics kind of idea is done in many other systems than power grids as well, including all kinds of complex systems in biological processes. And so it could well be that one could do something similar there as well. Yeah.
Okay, thank you very much.
Yeah, my question has to do also with that Q Gaussian you showed at the beginning.
Yeah.
So that Q Gaussian seems to have the right amount of tails to match the fluctuations of the frequency, right? And you said that I understood correctly that you get those statistics when you combine different processes that have different variances.
Yes. Yes.
So a combination of processes with different variants will give you that Q.
Yeah, a simple Gaussian process where the variance fluctuates. So you have for a while, this is precisely right. You have a stochastic process that is a Gaussian, and then in the next step, it's much broader Gaussian, and then maybe it changes back to a very sharply peaked Gaussian. If you integrate all that up and assume a reasonable distribution of the variance, then you get heavy tails out of that.
I'm asking that. Okay, that's very interesting, because I'm asking that because we once proposed a very simple model of devices switching on and off.
Yes.
Okay.
I know your paper. Yes, that's.
And those devices switching on and off seems to reproduce well some statistics of the frequency fluctuations, but not the tails.
Not the tails.
But in our case, since we just put one parameter, so it was just one process, it was like quite Gaussian.
So maybe if you let that parameter fluctuate, then you can reproduce
we would allow the size of the variance of those fluctuations vary on time, for instance.
Yes,
in average,
exactly.
we could get those. That's very interesting. We can talk about.
Could be. Yeah.
Thank you.
Do you have any mechanistic explanation on why the perturbations propagate diffusively in a big?
Yeah. Well, I mean, no, we just looked at data, but I presume these yeah, why the perturbation diffuses and is not moving in a straight line. Well, the power grid, of course, it needs to follow the electricity lines there, which are probably complicated system, but I don't know why that is. Yeah, it's just an observation. It's a kind of diffusion process on a large scale. Yeah.
I think the prediction, right, of the fluctuations is very important. Or prediction of the demand at a given time of the day is important for the company.
Yeah.
So besides your models or models that can be used, nowadays it's very fashionable to use blind machine learning algorithms. Yeah. Has that also been used here? And have they been
So this my former postdoc Benjamin Schäfer is going more and more into that, and machine learning is one thing, and then it's suddenly artificial intelligence, and it sounds great. And no, I think it makes sense in this case. If we could really improve these demand functions just by 10%, it would be an immense financial progress and environmental progress as well. So I think one should really take machine learning and AI very seriously there. If you can predict or forecast these demand patterns in only a slightly better way, it will be immensely useful for the environment.
Okay. Any other questions?
One question is, which to me is still not clearly understood, is the asymmetry on the fluctuations. Why the skewness?
Yeah.
Because if you take many of these models and you plug it into the swing model or whatever, you usually get symmetric fluctuations.
Yes.
The fact that there is this skewness is not a clear. To me, it's not clear what is the origin of that.
Yeah, I share your question. It's amazing. Why is it asymmetric? I don't understand it either. Yeah, and but I can tell you, in early days when I worked on turbulence, they also see asymmetries in turbulent systems as well. So there's a slight asymmetry there. In turbulence, it usually had to do with the boundary conditions of the system. So you have not infinite Reynolds number, but your container is finite, and that led to a sort of asymmetry. So maybe it's a similar effect that power grid is finite, or so. I don't know.
Models of the
models are symmetric.
Any natural model will give you symmetric fluctuations.
Yeah.
No. No, that's my point. I mean, what is the mechanism in the real data that might give this asymmetry?
Yeah. Because then one could construct better models that are slightly asymmetric. Yeah.
Any other questions? If not, we thank Christian again.
Okay.
Very nice talk.
Oh, it was a pleasure.
I have to leave now.
Yeah, I will answer your person. I put you in CC. No.